Now, so far, we've been considering alloying elements that substitute for aluminium, but we need to consider hydrogen, particularly in welding and in other processes. Now, hydrogen is such a small atom that it can exist in the gaps between the aluminium atoms, hence it forms interstitial solid solutions. Remember that when we substitute an alloying element for aluminium, we call that substitutional. Now, hydrogen is interstitial solid solution because hydrogen exists within the grains of aluminium. Now, hydrogen atoms are extremely soluble in liquid aluminium, but have very, very low solubility in solid aluminium. And that has big implications when we are solidifying aluminium, particularly in welding. So far, we've considered alloying atoms. Now, alloying atoms substitute for aluminium in the face-centered cube, substitute for aluminium in the grains, and they share the electron clouds. So alloying elements can form the metallic bond with aluminium. They increase the strength of the grains because they distort the grains, they change the strain fields of the grains. So alloying elements form a metallic bond with aluminium, and they change the properties of the aluminium by strain fields by affecting the lattices of the aluminium. Now we need to consider inclusions. Now inclusions are non-metals. They're ceramics or a metal compound. For example, aluminium oxide is an inclusion and it is a non-metal. And because non-metals do not form a metallic bond with the parent lattice. So inclusions are things that do not form the metallic bond with aluminium. So they are predominantly oxides, silica, sulfides. So inclusions do not form a metallic bond. Predominantly, they are oxides in aluminium. And inclusions have a different bonding. So inclusions form ionic or covalent bonds. Don't worry about what they actually are, but inclusions have a different bonding mechanism to metals. Metals form a metallic bond. Inclusions have different bonding structures, and inclusions are predominantly oxides, so they are ceramics, non-metals. They do not form a metallic bond with the aluminium. And because they cannot form a metallic bond, it means that inclusions do not bond within metals. They exist within the crystal lattice, within the grains, as a foreign body and impurity. So inclusions are not bonded to the metal lattice. So inclusions weaken the lattice and they can act as paths for cracks, reducing ductility. So if you have aluminium oxide, the oxygen has bonded to aluminium. Oxygen is not a metal, so oxygen has bonded with aluminium to form an inclusion. It is a ceramic. Because it has formed an oxide, that aluminium oxide, that ceramic inclusion cannot bond with the aluminium in the grain, so it's an impurity within the grain. It's a foreign body. Now, most inclusions are brittle in nature. Inclusions are predominantly oxides, so electrical insulators, so can affect the conductivity of aluminium. And most importantly, because the bonding has changed, inclusions have much, much higher melting temperatures than aluminium. Aluminium melts at 660 degrees C. Aluminium oxide, the inclusion, has a melting temperature of over 2000 degrees C. So inclusions of foreign bodies within the aluminium oxide, copper oxide, tin oxide, iron oxide. They are ceramics. They cannot bond with the aluminium, so they are impurities within the grains. They weaken the grains. They can act as crack initiators or crack paths. They affect conductivity and have much, much higher melting temperatures than aluminium. It's so important that you understand that inclusions cannot form a metallic bond, so they weaken metal lattices. And because inclusions tend to be brittle and tend to form localized concentrations, they can cause cracking and lead to failure of the metal. I've mentioned aluminium oxide, and this is so important. The most stable form of any metal, including aluminium, is an oxide. An aluminium oxide is the natural state of aluminium in nature. Aluminium oxide in bauxite. Now, aluminium has an incredible affinity for oxygen and readily reacts with oxygen of the air. Oxygen is what we breathe in air, and aluminium coming into contact with oxide reacts to form aluminium oxide. And aluminium oxide is alumina, and you will learn to hate alumina. So aluminium reacts with oxygen of the air to form alumina. Now, alumina is a molecule. It's two aluminium atoms bonded to 3 oxygen atoms. So when aluminium reacts with oxygen, 2 aluminium atoms come together with three oxygen atoms to form a molecule, alumina. And aluminium is so incredibly reactive with oxygen, it will form alumina virtually instantly. So if you scratch aluminium, by the time you've walked away, that exposed metallic aluminium will have reacted with oxygen of the air to form alumina. Now, the alumina is actually very, very important because the alumina passivates the surface of the aluminium. It gives it the important property, corrosion resistance properties. So the surface of any aluminium that you see anywhere has a thin layer of alumina, aluminium oxide on the surface. Aluminium cannot exist in air without forming this very, very thin layer of aluminium oxide, alumina, on the surface. And because it reacts so incredibly quickly, the aluminium oxide is self-healing. Now, we need to understand the nature of aluminium oxide, alumina. The surface of any aluminium that see will be aluminium oxide. So aluminium oxide, 2 atoms of aluminium, 3 atoms of oxygen bonded together. Aluminium oxide is called alumina. Now, the bonding of alumina is ionic, not metallic. So alumina, aluminium oxide in metal aluminium in a metal grain is an inclusion. So the presence of alumina in aluminium weakens the metal lattice. The aluminium oxide is self-healing, and is so important that you comprehend the fact that if you scratch aluminium, by the time you've walked away, it will have reacted with the aluminium to self-heal itself. Now, alumina is a ceramic, aluminium is a metal, aluminium oxide is a ceramic, not a metal. Alumina is very, very brittle. It has very, very low ductility compared to aluminium. So if you've got alumina in aluminium, it will reduce the ductility of the aluminium. Aluminium oxide is a electrical insulator. So if it's in aluminium grains, will reduce the electrical conductivity. And alumina has extremely high hardness, much, much stronger than aluminium, but it is much, much brittler than aluminium. And it has an incredibly high melting temperature. Alumina melts at over 2000 degrees C, aluminium at 660 degrees C. And again, we need to realize that aluminium has high thermal expansion, but alumina has low thermal expansion. So if you got alumina within aluminium that is being thermally expanded, the alumina can start cracks. So alumina is we need to consider alumina, aluminium oxide when we're talking about welding, rolling, because in any process that we have aluminium, as soon as it comes into contact with oxygen, it will form alumina, a surface oxide, and that alumina is totally different to aluminium. So alumina, aluminium oxide in aluminium is an inclusion. I hope you've enjoyed this module. I hope you've learnt something from this module. Here's some more reading for you, and thank you very much.